Okay, in this lecture what we're going to do is look at our first example of animation, and it's going to be a fairly simple example, at least as far as the graphics go, but we're going to have to examine how things work within the web browser and how the buffers work and how we can actually animate in a smooth way, and we'll see a number of options, and then in the next lecture we'll introduce how we get input from devices like a mouse and a keyboard. The key to this is functions which respond to events. So instead of having a function like in the old days where we would have some function in our program that was called something like a wait event, and then when an event happened it would trigger something and then you'd respond to it. Instead what we're going to do is use a model that first became popular with the X Windows system, which was to have a set of functions which were in the Unix literature called callback functions. In the browser literature they're called event listeners, which tell how to respond to specific events. And they could be window events, they could be mouse events, keyboard events, whichever ones you want to consider. And for each one we're going to have a callback or an event listener, which we're going to put in our JavaScript file, although we can also put it in our HTML file, and that will tell us when that event happens, this is what we want you to do. Now, the browser itself, we're going to look at the browser execution model in a second, is sitting there in an event loop, and it responds to those events for which it has callbacks. And the terminology it says when you register a callback with the operating system when you define it. So let's look at a little picture, a very sort of high-level picture of what happens when you're executing your browser. So if you look at what happens, you start off with your calling some sort of URL or clicking on a URL. And where is that URL? Well, here's the client-server model. Your program is a client, or you look at your browser as being a client, and there's a web server out there where the page is. So you click on that URL and a web page is loaded. That's your HTML file. And the JavaScript files in it, which is the part we're going to focus on, which describe what you want to happen, the action, the graphics. Go through a JavaScript engine running in your browser, and eventually as we've seen, we send information out to the GPU, which goes in the frame buffer. And the frame buffer you can think of as being part of the HTML5 canvas. In fact, it's really an image of what's in the frame buffer. The frame buffer is actually hardcore memory that's on it's probably on your graphics card, and it's really the display process that's putting copying what's in the pixel colors into an area of the canvas. But we can think of that as just being the frame buffer here lying within the canvas. And the importance here is there may be other things that are going into that canvas which have nothing to do with your WebGL program. So let's look a little more detail of what happens when you're working within that browser environment. So we start with the HTML file, which is what's pointed to by that URL. And what does that do? Well, it has a couple of functions. One, it describes the page, the canvas, what size the canvas is. It could describe where that canvas goes. It can also describe other windows that you might want to open, or the interactive devices that we're going to start talking about in the next lecture, like putting a button up on the display or a slider up on the display. So it's describing the page that you see. The HTML file, we're going to put the shaders in the HTML file, but there are other ways to do that. But the important things is, one, it describes the page, and two, it loads in a sequence of JavaScript files which have the application that we want to run in them and all the utilities we need in our matrix vector package. Now, the way that this works is these files are loaded asynchronously. And as they're loaded asynchronously, you have these script tags that say, okay, here's a JavaScript file I want you to load, and you load them sequentially, and then you're done loading. Well, what happens? Well, the browser is sitting there in an event loop. That's its general way of functioning, and it's waiting for an event. Well, there has been no event yet. So you've read in these files, well, actually there is an event, but we're not using it yet. But you've read in these files, and nothing is going to happen. Well, why doesn't anything happen? Basic reason is that what we've been doing is putting all of the things we want to happen graphically into functions like the init function and the rendered function. And if all the browser has done going through the HTML file is load those things and go through to the end, you're not going to see anything happening because those functions are never going to be called. But there's a very simple solution to this, which is called the onload event. So when the files are all read and you're at the end of that JavaScript file, that generates what's called an onload window event. It's part of the window object that's within that browser. And we can say, okay, when that event happens, now I want you to execute that init function. So for example, we have in our code, in our JavaScript examples, WebGL examples, we have things that say something like window onload equals init. Now a couple things to notice about that. Here's the function init, which we put our initialization in, and that eventually calls the render function. Also, this variable window is defined outside of our code. This is sort of a global variable that's defined with the window, so we don't have to worry about it being defined. This is one of the features of HTML, and it's particularly JavaScript that says there are these variables defined outside of the program because everything is an object. So we can say window onload equals init that says when everything's onloaded, that event happens. Now execute the init function. So let's do a little example of that and see what else we have to do in our code. So a simple example I have is a rotating square, and there are various versions of this on the website. I'll run some of them in the next lecture, but it's a very simple example. It says, okay, if you have a point on the unit circle, so it has coordinates cosine theta, sine theta, and you can see that's obviously on the unit circle because cosine squared plus sine squared equals 1. You also have the three other points, minus sine, cosine, minus sine, sine minus cosine. They're also on that unit circle, and in fact, they're equidistance apart, and this is defines the vertices of a square with sides of its length square root of 2. So you can say, well, one way to get this rotating square is to keep sending out new points out to the GPU with different values of theta. So here's a very bad way to do it because it's so slow and it's violating all the things we said we want to do, but it's at least going to get us started. So suppose we've defined our buffer up outside here as part of init, and then we're sitting there in this loop, and we just keep going through this loop any some number of times, which what it does is increase the value of theta and then generates new points that we put in the same vertices into the array vertices, and then we send that data out again. Well, and then we render it. Well, that'll work. I mean, because each time you're putting 4 different values along that unit circle into that same array on the GPU, and every time you run the render function, it's going to render those. Well, that's not such a hot way to do it because we said, no, we don't want to keep sending data out to the GPU. So a better way would be to just let's send some vertices out and then send theta out. So start off with the vertices at 4 convenient points like 0, 1, 0, 0, minus 1, 1, 0, and minus 1, 0. Then send theta out to the shader and do a rotation there that compute sine theta and cosine theta for those values of theta that I send in, and I use what's called a uniform variable to say that. And then how do I render that? Well, I can render in some sort of recursive way. Each time I do the render, I call the render function in there. So the idea would be to try and do something like this, that first here's the uniform variable that I set up. I'm going to call it theta in the vertex shader. We'll get to the vertex shader in a minute. And then I get its location after I've compiled and linked everything together. Now let's jump down to the render function, which says, okay, increase theta each time you come through by some amount. Then send that new value of theta over to the vertex shader. And now draw the arrays again. And in the vertex shader, I'll use that theta to compute the new positions because I can always change positions in the vertex shader, and then call yourself. So it looks like, and we're going to have one little caveat here, that this won't quite work, but it's pretty close. So we're essentially sitting here in an infinite loop, generating new thetas and re-rendering that triangle strip. Okay, well, let's look at the vertex shader before we get to what's the problem here in this little render function. Okay, so here's a real simple vertex shader. It says we have attributes again, which are the 4 vertex positions which have been sent in. I say that theta here is a uniform float, and now I compute new positions from the original positions, v position. I now apply a transformation, which is equivalent to a rotation, which converts them to the 4 points on the unit circle. I set the z value to 0, the w value to 1, and that's my little vertex shader, and the fragment shader can just set the color to a constant color, and that's enough. Well, this won't quite work for the following reason. We are re-rendering the square. We're sending that data over and over again, and we're always running the vertex shader again. But the problem is all that information is going into a buffer which we don't see. It's not the color buffer that's being displayed. And the reason is that the browser is using a technique called double buffering, which used to be optional, but now it's absolutely standard because the memory to have 2 buffers now doesn't really cost you much. It used to. So the idea is this, that we're trying to avoid seeing jerkiness on the display, and we're especially trying to avoid seeing a partially drawn object on the display. The reason is that the display process is happening independent of our code, which is generating the vertices and trying to render. So the trick is that we always render into a back buffer. We always display a front buffer, and then we have some mechanism to say, okay, now is the time to swap the front and the back buffer. So the back buffer becomes the front buffer, which has the new information in it, and the front buffer becomes the back buffer, so we clear it and we can render into it. So this cell will never see a partial display. Notice that this, if you think about this, you're not doing anything any faster or slower than you were doing it before. It's just preventing seeing a lot of junk up on the display when you're only seeing part of something, because either what you're drawing takes multiple display cycles to draw, or that these 2 processes are not synchronized together, so you're seeing part of a display when you actually see a new display up on the screen. So the trick is, how do you trigger this buffer swap? Because we weren't doing that by just generating the renders, and the trick, of course, is not really a trick, but it's saying you need an event. So let me give you 2 options for generating an event that will switch the front and back buffers, and then we'll do that within the render function, so we won't switch the buffers until we put the new data onto or actually take the existing data that's on the GPU and have the new theta out there. Well, the 2 ways to do that is to have a timer of some sort, and at the end of that timer, an event will be generated and a buffer swap will automatically happen. The other is to use a function that's supported essentially on all browsers, which is called request animation frame. So let's look at those 2 options. Okay, so an interval timer is something that says, I'm going to run a function that I'm going to write the code for after some number of milliseconds, and when that's over, it's going to generate an event which will cause the buffer swap. So it just says, here's set interval, here's the function I want to execute, which in our case is render, and give you the interval in milliseconds. So something like 60 milliseconds would be approximately 60 frames per second. Also note that we should have pointed this out in the last slide, that the buffer is being redisplayed automatically at about 60 frames per second in your browser. It used to be exactly 60 frames per second in the US because it was coupled to the line frequency. And in Europe and other places it was 50 cycle times per second. That's now not a requirement in any of the modern hardware, but it's set in most browsers to be about 60 frames per second, and some of them will let you adjust that rate. If you have things that really need fast, usually your displays are capable of displaying at a much faster rate. Okay, but let's go back to the set interval function. And so we can set the interval and then do a buffer swap. If we set it to 0, it's going to say just do buffer swaps as fast as you can, which will generally be about 60 frames a second. And there's you can actually put a timer in. I think that's in the notes to really see how fast you can really do it in your particular browser. Okay, so here's now a way of doing it here. We could do one with the interval timer. The better way is probably to use request animation frame, because that's tied in to the browser, and when the browser is collecting events and trying to do it, it says, okay, the next time you're ready to do an automatic buffer swap, then I want you to execute this function, which is render. So again, it's recursive. It's incrementing theta as every time you go through. It's getting the uniform variable, and then it's incrementing theta, it's sending it over as a uniform variable, and then it's drawing the rays and says, okay, request an animation frame. So essentially, this is a way of putting this in an infinite loop of render as fast as you can, locking it to the rate at which the display goes. If you want to now combine those two techniques, you can make the display go faster or slower, and we'll see how we do that more in the next lecture. But you can put an interval timer inside to, at least for now, let's say slow it down. So we can put an interval timer in here and say, okay, what I want you to do is wait 100 milliseconds before you do this. So we can request an animation frame, and then we could say, okay, I'm going to get a new theta as a uniform variable, send it over as a uniform variable, and then I'm going to draw arrays, but I want you to wait 100 milliseconds before you do that. And in the next lecture, you're going to see how we use that technique to do things like speed up or slow down the rotation of that square, and I'll demo some of those. But you can actually look on the website under Chapter 3, and there's various versions of rotating square on there.